not calculus, chemistry in the AM is here, live and in person and on recording. We just went through the first of yesterday's example questions. Boy, that's looking, yeah, I know, that's kind of odd. But anyways, let's say what I have. It's getting all goofy. I thought that would solve it. Okay, so the barium hydroxide. The hydroxide, treat it as an arenas phase. Just break it up, don't worry about water. Barium hydroxide starts as a solid, breaks up into these two lines. Look this up on an iron chart if you want to know. This is a 1:2 ratio from barium hydroxide to 2 hydroxide. So we're told that we have 0.37 molar ammonia. It's going to double. So what I do is concentration of hydroxide. That's what I then switch. Repetitive because we're using the KW expression, so it just ends up being 10 to the minus 14 divided by the other end. That's where this. Now I wouldn't normally put arrows on my word short. Real work is coming out with the equation. Defining the HCl equation. Acids are way easier to locate. So I've done my water as well. Acids will add to water. Strong acid, so we get H3O. All right. Actually, I have this on the first page. That's a 1-to-1 ratio, but that's why we really have no calculation. HCl all goes 100%. And then the last calculation. And the KW expression always comes out to be the 10 to the minus 14 divided by the 1. Which gives you the answer. I'll pause for a minute. Now you are. Welcome aboard to Weak Acids. In case you're just joining us, this is Chemistry in the AM. Here it is, 3 minutes later. Okay. Calculating the hydronium ion and hydroxide ion concentration with a weak acid. Strong acids go 100% one way, so they're simpler. Weak acids mean 2 directions. That means equilibrium kind of stuff we have to do again. So we've done nothing but equilibrium in this course. You're going to use a Ka value from that chart if it isn't given within the problem. And when I say that chart, the one on your handout set, right? Okay. So you're going to need the handout set. I'll give you a minute to get that out. I'll pause the video. We got our handout sets. Okay, good. We're going to use it during this problem. Calculate the concentration of hydronium and hydroxide ions. Okay, that's the same as before, but it's a weak acid, and we got 0.0560 molar solution. I'm going to do this one way now, but then you're going to see, oh, there's a short thing. So like when you guys did quadratic equation problems. You know how initially, if you're a Greek algebra, so you did something called completing the square, and it's like, okay, you do this again and again, same steps always. Here's a quadratic equation, negative b plus or minus zero. Oh, that's a shortcut. Save it somewhere. It'll be like this. So we got HCl. put HCl down. That's no good. HCl. It's an acid. We're going to add it to water. It's equilibrium. It's weak. Really. Okay. When it breaks up, its job is to give away the H from the front of the HCN. So it becomes CN, and you can look it up, it's negative, but it's CoH plus 1. So you probably don't need it. And we've got our H3O. Hydronium ion concentration. Okay. So there we are. That's the first thing you do, even when we learn the shortcut. You've got to do this. I'm going to do an ice chart. Margin. Water, and I didn't put that down, so it's pure liquid, so it's not going to appear in my ice chart. To start with, we'll imagine that this is the very second got these bowls and I haven't started mixing. So we're going to say 0, 0, 5, 6, 0. It's a 1-to-1 ratio between HCN and H2O, as well as the cyanide INCN. So if one HCN breaks up, you get one CN negative and one H2O positive. Right? If X moles of that break up, minus X, right, minus X, we got plus X. And we know that 0 can only go up, so that works. There's no doubt about it. That's the plus. We do the arithmetic for the equilibrium one, 0 plus X. Now this is our moles per liter here. We've got an algebraic expression. Now, because of that 0.0560 minus X particle, that means we're going to have to use the quadratic equations, which we could do, but I don't do it. But you know what? You're going to notice that it really makes very little difference anyways. Here's the thing. We've got to assume this is a weak acid. What you do, you're going to write these down. Assume X is small. So for example, if I assume that X is small, so like 0.0056 minus. If I had, don't write down this at the bottom. I'm just showing you what I mean by assuming. If I had 0.00, a number like that, if I subtract those two numbers, does it really change the 0056? No. So we're assuming that you're going to get a small number. Why can I assume that? Because it's a weak acid, and when we look up the Ka value, it's like 10 to the minus 10. It's going to be in this range, like when we solve it for the acid. So I'm just showing you why this works. Just use 0.005. You have to state to make it. Okay. Because it's strong. And I won't try to fool you and give an acid that's just kind of in between. Yes, if it's not one of the 6 strong acids, it's small, and you can make this assumption for any problem I give you. There's some that aren't, but I'm not going to give you. Yes? Basically, if it's an equilibrium acid-base problem, it's weak. Yes. And I'm not going to try to fool you with something that this assumption is.
And there's no other.
There's only the 6 strong acids, and I will state those.
Okay.
Okay, yes. Okay. That's usually an indicator, not always, but yes, HCN negative. And you can look it up. We're treating it as an acid. Okay. We're going to use 5. Okay, now I'm going to get back to the problem here. A Ka expression. Now I use Ka. It's K equilibrium, but because it's an acid problem, we're going to just call it Ka. So and that's the same way we always did expressions. Cn negative, that's part of it. H0 positive. Yeah, I always have my back to it too. I'm in your way. You want to move. So there's our expression, right? And this is why you have your ion chart, your Ka value chart, equilibrium. You're going to look up HCN on that chart and find the K value. It's towards the bottom. It's 10 to the minus 10 in that range. That was going to tell me. Find the Ka value for HCN. HCN would be like a TV channel. The Home Chemistry Network. This is, you're watching this. In case you've just joined us, this is Chemistry A&DM on HCN, Home Chemistry Network. I'm waiting for an HCN value. I'll keep waiting. It's taking a while because this list, my other list, it is on. Okay. 6.2 times 10 to the minus 10. I promise you, if I give you something on a test, it'll be on the list.
Yeah.
Oh, yeah, I will. Okay. Then we substitute our E-line values. So the CN concentration, we're going to use X. And then the H0 concentration, we'll use X. We're not going to use 00560 minus X. We're going to use, as we said, 0, 0, 0. Minus X doesn't really make a big difference on that. No, it's going to be so tiny. Mathematically. There's no multiply. This is just what. Right. That's to make our math easy. Otherwise, you have to use the full-blown quadratic. Which you guys can do for most people. Not everyone's taking it pretty up there. So, you know how to solve this. This is an x squared on the numerator. I'm going to multiply up my 560 for just a second here. 6.2 times 10 to the minus 10. Gosh, I hit my pen times 0.0056 equals x squared. How do we undo an x squared? Square root. You're actually going to multiply those two numbers under the root. You can multiply them first and then hit square root. It's 2.47, I guess. Oh. 3.47 times 10 to the minus 12. And you should get 1.86, 10 to the minus. All right? So we'll use, how many significant digits though? Because we had 6.2 going in. I'm going to just use 1.0. Okay. Okay, you got to just count the decimals. There's 5 zeros in between. You're a smart person. You do it now. Okay. So X was in place for Cn negative and for H3O positive. We wanted the hydronium ion concentration, so I'm going to declare that right now for unit. Okay, we've got this part solved. And I just heard we have to do the concentration of hydroxide. That's an easy thing. Yes. Question first. Okay. I'm going to just set up everything and then I'll zip back to sleep. Okay. So the hydroxide concentration, 1 times 10 minus 14, because that's a repetitive thing. You get it enough, you know why. Divided by the other answer. You'll get the concentration hydroxide. Or it ain't working with the tubes. What are we getting? 5.3, I think. 10 to the minus 9. We've got both things there. I'm going to pause the video and quick check on these. Okay, I told you there's a shortcut. And I'll show you it in a second. Is there a shortcut? Yep. There is. Now, here's how we're going to come up with this formula, and we'll see how it works. We'll show you how much work you can save. For any weak acid, so I just had A like a variable. H attached to A, not an actual element. We know it breaks up in, when it's added to water, acting on acid. And it forms H0 in a 1-to-1 ratio. So whatever it is, and I'm going to fill this in UR2. We're going to just say whatever number you get for the concentration of H. We're going to subtract X, and it always becomes HA minus X. Concentration of H. And S X. So this is for any X. And then we make that assumption, assume X is small. You just plain old concentration. I googled it up and it said people sound on time. You're better on a phone to Google up how to. Okay. We won't do it now and also. But yes. Oh really? Okay. So now what? We do our Ka expression. And you know how it's A times, well, I'll just write it. Say it. You know how to do these expressions. Pass it on the bottom. And then we plug in our stuff. Ka value, which you look up on a chart or be given in the problem. X and X make X squared. And it comes out to that. This is what we did with numbers. We know that the X squared, I'm going to left right first, equal to K times concentration of the acid. We know we have to do the square root. And the square root will give us the hydronium ion concentration. This is our shortcut. But it's only Sure. Yep. Just like when we did this before, where did H3O come from? Our X is in place of H3O, right? And so when we solve for X, by taking the square root, we're really solving for H3O. Okay? That's a good question. I'll just mention, and we won't go through the whole calculation where it comes from, but you're going to put this down underneath. If you were given a K, for a base, is it a surprise that they call it a KB value? So KA. This is the same thing. You're not going to use it on the test, but have it on one of our assignments. KB value times the hydroxide. It's the same formula. We just trade in all the acid things for base. What did I do there? I did something wrong there. I put OH there. That's wrong. Concentration of the base. Concentration of the acid in the red and green base. Okay. So we flip back to the previous page and try out the shortcut. I would still require you, if you're using the shortcut, to come up with the equation. We need that. But this shortcut will save us continue all of this work. Turns a one-page question into just 3 lines. Here's our shortcut. We'll use that. So you know how it's said. H3O positive equals the square root of the Ka value and the concentration of HA acid. I'll just put the word acid. That's the shortcut. We want the H3O, hydronium ion concentration. I'm trying to squeeze it in because I don't have a lot of space. I'll just give it a little more space. Square root. The Ka value we looked up on Google, 6.2 times 10 to the minus 10. M. The 10 to the minus 10, I was trying to squeeze this in here. 0.00560. You notice that's our last step, more or less? You just calculate it correctly and you get your 1.0. Okay. You see what the shortcut does for you? It eliminates the use of an ice chart, makes use of that assumption that X is really small, and if we look back on this X, did our assumption hold? 1.9 times 10 to the minus 6. I just made up an example. But if you take this, 1.9 times 10 to the minus 6, it would be like subtracting 1. 0, 0, 0, 1, 2, 4, 5, 3, 4, 5, 6. If I subtracted that from 0.00560, does it change it? No, it's still 560-ish, right? The assumption holds true, right? I just made up a number earlier and made it way smaller, but I'm showing you that this assumption is good. Okay. So, what do you need to do? Well, I've got some problems for you. And I've got the answers for you too. I'm going to hand them out right away. If you're on video, I'm just going to show them. You can pause the video and jot them down. Just for the video people, pause, type stuff, try it out, and then check your answer over. Just for the video people. Pause, copy down C, try it out. There's the answers. And lastly, number 2, try it out. Pausing, write it out, try it out. Here's the answer. Okay, please show the answer here slowly again. Okay, good. Over and out with the video. We've got work.